Welcome to Neil Shaw Physics. In this video, we will be solving a problem from Irodov's book of General Physics. This problem is 1.9 and says, a boat moves relative to water with a velocity which is n is equal to 2.0 times less than the river flow velocity. At what angle to the stream direction must the boat move to minimize drifting? So with these problems, the first thing that we have to do is draw it out. So here I am drawing the banks of the river, and let's say the boat has to cross a distance of d. Then I will draw the vector for the flow velocity of the river, and then this is the vector for the velocity of the boat. And the drift distance will be distance r. So v is going to be the velocity of the boat if it were in still water. So the vector v is going to be equal to some velocity component in the x direction and the y direction. Next, we look at the flow velocity of the river, which is v naught, and it's still a vector, except it has no y component, and the x component is just going to be v naught. And then it is stated in the problem that the river flow velocity is equal to n times the magnitude of the velocity of the boat. So both of those are magnitudes. In order to find the drift distance, the first thing we need to do is find the time. So we could find the time by using the vertical distance. So the time it takes to cross the river is going to be that vertical distance d divided by the velocity in the y direction. This is just a rearrangement of the equation that distance is equal to rate times time. Next, we can use the same equation, but then apply it to the x-axis. So the distance is going to be r, and that is going to be equal to the velocity, which is going to be the sum of the river flow velocity and the velocity component in the x direction of the boat, and multiplied by the time. However, from using the equation in the y direction, we have the time in terms of the y component of the velocity, so we could rewrite it as so. And then from there, I can just distribute to get that the drift distance is equal to the river flow velocity times d over vy plus vx times d over vy. Right now we have a lot of variables, so we want to try to minimize that by putting it in terms of something else. So when we are dealing with components of a vector, one way that we could easily relate it to the magnitude is with the angle. So let's call this angle theta right there. And this is going to be the angle between the positive x-axis and our velocity vector of the boat. This means that we can rewrite our expression for drift distance in terms of theta and just the magnitude v. So we could rewrite it v naught d divided by, and vy is going to be equal to v times sine of theta. And then we can add that to vx, which is going to be equal to v times cosine of theta. Then d is left the same, and then vy again is v sine of theta. So immediately you will see that the v's cancel out in the second term, but there is more simplifying that will happen. Remember that we have on the left that v naught is equal to n times v, so we can just make that replacement in the first term, and then we will see that there will be v's that cancel out. And then we can add that to d times cosine theta over sine theta. With most minimization or optimization problems, there will usually be a derivative involved. So we know that there will be some theta where r, the drift distance, is going to be the least. This means if we imagine r as a function of theta, which we can see on the screen, In the domain from 0 to pi, there will be some point where it reaches a minimum and then increases again, which means that the slope at that point is going to be 0. Luckily, we can find the point where that occurs by taking the derivative of r with respect to theta and setting it equal to 0. Writing this out, we know what r is, so we could write d over d theta is equal to d times, I just factor out a d, times n over sine of theta plus cosine of theta over sine of theta. And all of this is going to be equal to 0. D is a constant, so I'm just going to factor that out when I take the derivative. Now, because I don't remember the derivatives of cosecant and cotangent, I'm going to use the quotient rule. The quotient rule says that the derivative of something over something else is equal to the derivative of the top part times the bottom part minus the derivative of the bottom part times the top part all over the bottom squared. N is a constant, so the derivative of a constant is always 0, so that part's going to be 0, and then you subtract the top part, multiply by the derivative of the bottom part, which is going to be negative n cosine of theta, and then all over the bottom part squared, which is sine squared theta. You can do the same thing for the second term. So firstly, you take the derivative of cosine theta, which is negative sine of theta, multiply by the bottom part, which is sine of theta, and then you subtract the derivative of the bottom part, which is cosine of theta, and then multiply by the top part, which is also cosine theta. And you divide all of that by the bottom squared, which is sine squared theta. And this is all equal to 0. So now I'm just going to rewrite all of this a little bit more simplified. And the first term inside of the parentheses is already pretty simplified, so I can just copy that and paste that over there. And then for the second part, negative sine squared theta minus cosine squared theta is -1. So then I could replace the plus sign with a minus sign and just keep the sine squared theta in the denominator. And then all of that is equal to 0 still. D is a constant, so that's not going to affect anything. I could divide both sides by D, and I might as well divide by a -1 as well because both terms are negative. So I'm just going to copy this part, and then I will change the negatives to positives. Now, if we look back at the diagram, we see that sine squared theta can never be equal to 0 because if theta is equal to 0, that means that it would never get across the river, making theta equal to 0 useless. So we can multiply both sides of the equation by sine squared theta. And then we get that n cosine theta plus 1 is equal to 0. And then obviously from there, everything's a constant except for theta, so we can just solve for that. N cosine of theta is equal to -1, cosine of theta is equal to -1 over n. The reason I kept it as n this entire time is because they could have chosen anything for this problem. They chose 2 in this case, but just to make the problem more general, I kept it as n. So in the domain of theta is equal to 0 to 180, cosine of 120 degrees is equal to -1/2. So scrolling back up, this angle theta is equal to 120 degrees. This angle will minimize the drift distance. If you wanted to solve for the drift distance, you can just plug in 120 degrees into our equation of r as a function of theta. That is it for this video though. I hope you enjoyed. Thank you for watching. Bye.